Hi there and welcome to our lesson 5 on our P5 spatial reflection topic, and today we are going to be looking at satellite communication and how we use electromagnetic waves to get TV, radio, not only that, telephone communication as well. Anyway, I will see you at the end of the lesson. I hope you enjoy it. Bye bye. Okay, so our objectives for today's lesson on satellite communication is that by the end of this lesson you should know and understand how electromagnetic waves are able to change direction when used for communication. Now, radio waves are electromagnetic waves with low frequencies and a high wavelength. Now, these are generally used for communication as they are very good at carrying different information. Now, if we look at this diagram here, we can see how waves are actually used, or radio waves are used in transmission. Now, we can see here the first wave is we can send it to satellites, either low orbit polar satellites or geostationary satellites. Now, the geostationary satellites tend to receive high frequency, low wavelength communications from the Earth. Now, the reason for this is because only waves between 30 megahertz and 30 gigahertz are able to pass through the Earth's atmosphere. Now, if they are below the 30 megahertz in the atmosphere, they will be reflected back by an area in the upper atmosphere known as the ionosphere. Now, any wavelength that is higher than the 30 gigahertz can actually be absorbed or scattered by dust, rain and other effects of the atmosphere, so we don't get that clear, clean reception by the satellite. Now, TV programs can be transmitted one of two ways. The first one is through radio waves. The second one is through microwaves. Now, if you have a TV aerial, you will get that through a radio wave. So if you have one of these on the side of your house, then you'll be receiving TV through a radio wave. Now, if you have a satellite dish like these, then you'll be receiving your TV through a microwave. Now, a satellite dish will not be able to pick up radio signals, and a TV aerial won't be able to pick up the microwave signals. Now, what a satellite dish does is it focuses the wave. Now, I'm going to quickly show you a diagram. Now, on this diagram, what we can see is the red lines here show the crest of a wave. Okay, now we've got the wave incoming, and you can see that there is a distinct regular pattern in the wavelength. You also notice that they're coming in straight. So what these microwaves will do is they will hit your satellite dish that has this shape here, and it will cause them to change their shape into this curved shape. Now, what happens then is that the signal coming this way will be reflected and focused onto the detector. That way that you can actually pick up the signal, and then you'll have the wire coming from the detector here going into your house, into your satellite dish box. Now, these dishes here can often be a lot bigger than the actual wavelength of the wave needed, and that's in order to capture all the microwaves and focus all the signals to the receiver. Now, this means that the diffraction, which is this bending here, remains narrow and focused, so the receiver will have to be well aligned. Now, radio waves can pass over and around objects by diffraction. Now, often when you watch films like Cliffhanger, they use radio communication because radio is the best ways of communicating through high obstacles such as mountains or hill ranges. So you might find that in some places they might not be able to get a telephone reception on a mobile phone, but they can get TV, and that's because of the signal sent by radio instead of microwaves. Now, how that works is like this. So as you get the signal sent, you can see the regular pattern. Now, as it comes into contact with the hill, it starts to change the speed in which the radio wave is moving, and that causes it to bend. And you can see that the direction of the wave, although we've got a regular pattern here, it's a bigger pattern here. So we can actually pick up the signal in this house that's directly behind the hill. So we've got no direct contact, but we've got the diffraction around the hill. Now, the amount of diffraction can change on the size of the gap, if you like, that it's got to pass through. So what we'll have a look at next is how we get those different rates of diffraction. Now, the first one we'll look at is where we get a large gap compared to the length of the wave. Now here we've got a large gap which is bigger than the actual wave length itself. So the length between there and there is smaller than this gap here, which means that the wave is only slightly diffracted here. Now, if we compare that with a gap that is similar to the wavelength, so we've got the wavelength here, the gap here is similar to that wavelength, we get a maximum diffraction, so we get a maximum curving of that wave. Now, the next one we'll look at is where we have microwaves. Now, microwaves here, we've got a small wave with an obstacle in the way. Now, as that microwave travels towards it, we get a slight diffraction, whereas with a radio wave that obviously has the longer wavelength, we get an increased diffraction as we hit that obstacle. So this is why radio waves work better than microwaves in areas where there might be lots of obstacles, such as a hill, mountain range, that sort of thing. Now, one of the advantages to this diffraction is it helps radio waves travel around the entire world. So very, very long radio lengths, such as the BBC Radio 2 on the long wave AM channel, means that it can have a wavelength of over a kilometre. Now that means that it can be easily diffracted over hills, and it makes their programs easier to pick up. Okay, so to review what we have covered today, we have looked at how we can use radio waves and the frequencies that are able to get out of our atmosphere up into satellites, and whether it's a low polar satellite or a geostationary satellite. We've looked at what happens with radio waves that hit the ionosphere, that section of the upper atmosphere. We've also looked at how microwaves and radio waves can diffract, and how radio waves are better at diffraction than microwaves purely because of their wavelength. Anyway, I hope you've enjoyed this, and I will see you next time. Bye bye.